Well, hello everyone. This is KEP the Math G once again. Getting ready to do another AP problem, AP calculus problem. I usually deal with the AB because that's what I taught, but I am trying to study the BC problems as well so that I can be well versed in those. But for right now we have a really nice problem here, and I want to say that I am not taking the credit for this particular problem, although I will take credit for the answer. I do want to show this came online. Okay, a few of these pages here. Someone wrote this out, and I tell you, he or she, whoever this is, they get all the credit for this. They put a lot of time and effort and energy into this, and I don't remember where I got the information from, but needless to say, we could evidently could make a copy of it, so we're able to use it, and we are going to do just that. This was done in 2017 on related rates, and this person has several related rate problems, and they really did a really nice job with those. I worked several of them, not all of them, but several myself. This is probably one of my favorite related rate problems here. We're going to do two parts, but we're just going to do the first part right now and then do the second part later, as each one will require some some explanation. Let me get this light situated over here, going this way. Alright, that may bring a little more light to the subject there. Let's go ahead and start with this. It says a weather balloon is rising vertically. Alright, so a weather balloon is rising vertically. Alright, so I'm just going to, I don't know, I'm not very good. Alright, it's rising vertically. Alright, and there it is. Okay, and it's at a rate of 15 feet per second. Rate of 15 feet per second. Let's stop right there. We usually say that vertical, when we talk about a vertical rising, okay, that, you know, your y-axis is also vertical, isn't it? So we're talking about a change in y, because this is y. So the change is the rate of change in y of this vertical rising is equal. So that's going to be referred to as dy over a period of time. Okay, and notice that that is equal to 15 feet per second. All right, and so that's what we have to deal with. And I want you to be able to understand right off the bat that that is dy over dt. It can't be anything else. All right, I already know where this is going. It says an observer stands 600 feet horizontally. So horizontally, this person is standing 600 feet. So I'm just going to say somewhere right in here. Well, let's see. How about, well, let's make it big enough where we can all see it. Again, this is not drawn to scale. I'm just going to have to write up here 600 feet. I just don't have room to put everything. Okay. 600 feet is fixed. This is along the x-axis. Alright, this is along x. So think about this. Since this is already a fixed spot right here, where this person's standing right here, it's fixed. So is there a rate at which this person is walking away, further away, or is this person walking this way, further in? The person is 600 feet. He's just standing there. He's staying there. So that's a fixed amount, which means that the rate that this person is walking Yes, there is none. I mean, that's zero. Okay. So if you want to say dx over dt, the answer is 0. But this is a fixed. So this here is 0. So we're not really concerned. If you want to put that, the rate at which this person is walking is 0, because this is a fixed amount right here. And that's what you got to understand. It is fixed. And anytime something is stationary, you're not moving further away from it, you're not moving closer to it, you're staying right here. 600 feet from the spot from where the balloon started rising. Okay. So really what we're developing here, it appears that we're developing a triangle. And I have very little room, limited room, so bear with me. This is going to be, and we're going to look at the rest of this sentence, but that's not straight. Let's try to draw it a little straighter. If I don't, I'm just going to let it be. There it is, right there. It says, when the balloon is 800 feet in the air. That's the instant that the balloon is that high up. So the instant, or the time when, or the moment, instantaneous, or whatever you want to call it, the instant that the balloon is 800 feet in the air. So that means that y at that instant is 800 feet. So we know that this height is y. We know that this length is 600. Okay. It says find the rate at which the distance from the balloon, so I guess maybe I'm just, well, okay, from the balloon to the observer is changing. This distance right here is z. And so it says find the rate at which the distance from the balloon to the observer. From the balloon to the observer. Okay, so we're looking for, so we're going to call this z. This is changing. This rate of z is dz over dt, which that's what we don't know. Alright, we're going to say this is z right here. Alright, so if this is z, we're going to call this dz over dt, and that's what we got to find. Now remember, this right here, dx over dt, is fixed, so once you say fixed, is 0. That's like a 25-foot ladder leaning against the wall. The ladder itself is not getting any longer or shorter on most of those problems. So if the ladder is 25 feet long, then that dz over dt in that particular case is 0. And you got to be aware of that. Alright, so let's set up our problem. I'm going to set it up right down here. We have, this is a right angle, so we can use the Pythagorean formula. So we have x squared plus y squared is equal to z squared. I might put a line through z. Okay. That's it. And that's what you got to remember to do. On these types of problems, you have a triangular problem, you're dealing with the Pythagorean theorem in this particular problem here. Now we got to find, since we're looking for this rate of change, we've got to take the derivative. So every time we take the derivative of each one of these variables, we are tacking on the dx over dt, the dy over dt, and the dz over dt. So I have to flip the board, but let's go ahead and start it. Get the problem started. 2x Remember, put the 2 in front. 2 times 1 is 2. 2x to the 1 dx over dt plus 2y dy over dt plus 2z equals 2z dz over dt. We can divide by 2 both sides, and we're left with x. Alright, 2 over 2 is 1. 2 over 2 is 1. 2 over 2 is 1. You could have left it there, but try to make it as simple as you can if possible. So let's look at this over here. Okay, let me flip the board. Bear with me, because everything's got to be moved a little bit. Okay, here we go. Yeah, you need to get out of the way. My wife hung that up years ago, even before I met her. So it's been there. Here we go. Alright, so bear with me as we said this. This was x dx over dt plus y dy over dt times, of course, equals z of dz over dt. Now keep in mind, we do remember we've got x squared plus y squared. And we know that x was 600. We know at the instant that y is 800. And we know that z squared, I will talk about this in just a moment. We're going to have to use this to find z. But we do know x already. X is 600. So I'm going to try to do a little bit of both. Remember, that's a fixed number. Dx over dt is not moving. No rate to it at all. If I'm not moving, there's no rate. I'm not going one way or the other. So in this case, that's 0. Keep that in mind. Y, we found that already. Oh, let's see. 800. Yes. 800. And we found that that is at 15. Okay, 15. I want to say that said feet per second. Yeah. Feet per second. That's the rate. That's the rate that was going. Alright. So equals z, which we don't know. dt dz over dt. So we don't know this yet. And we don't know this yet. Alright. Well, we need some room, don't we? Sorry. Alright. Equals z over dt. We gotta find z. And then we'll be able to find dz over dt. We know this is 0. So really all we're dealing with. Alright, 8. We'll work on that just a little bit. Well, let's find out. Now look, there's some way of figuring this out pretty fast. There is a 3, 4, 5 triangle. Right? Be aware of that. 3, 4, 5. Your 2 legs, 3 and 4, your hypotenuse is 5. 3 squared plus 4 squared equals 5 squared. Evidently, if I were to double that times 2, we would have 6, 8. We would have a 6, 8, 10 triangle, wouldn't it? 6 squared plus 8 squared equals 10 squared. So, if we make this 600, 800, then what do you think this is going to be? Just add 2 more zeros, right? So this is actually 1,000. we could figure this out. We could do all the arithmetic here, but z squared, well, actually z squared, that would be what? Oh, I don't know. I didn't figure that out. Let's see. I think you just gotta, let's see. 1, 2, 3. I think it's 1 million. Okay. And then when you take the square root of 1 million, you get 1,000. And I know that says, you know, you can use plus or minus, but since we're dealing with positive units, we don't worry about the negative side of it. Okay? And just to kind of clarify that I am correct on that, I do have my calculator handy, so bear with me just for a moment. I don't think I need it, but there it is. So let's see, 600 squared, well, let's see, okay, 600 squared plus 800 squared, okay, yeah, that is 1 million. And then enter now square root of that. Oh, let me just put it in. Yeah, it's equal to 1,000. You know, being at my age, I guess you have to clarify things. I want to be right too. If I say 1 million, then this should be 1,000, right? Because you just actually triple, whatever, how many, you double the number of zeros is what you do. All right, so that is going to be 1,000 there. So now we're able to work a little further. Let's continue then. All right, so we know then that this is 800 times 15, and let me multiply that out. So bear with me there. 0, 0, 8 5 is 40. Okay. And then 0, 0, 8 times 1 is 8. 0, 0, 8 5 is 40. 0, 0, 1 is 8. So 4 plus 8 is 12. Yeah. So 12,000. Okay. Alright, so 12,000 is Z. Alright. Wait a minute. Oh, that's this right here. Okay, that's right. So this right here is 12,000. And that's equal to 1,000. Z is 1,000. dz over dt. There we go. Boy, we're getting it down now. Yeah, and that is, I do remember that answer is correct. That's going to work out fine. Now, the only thing left to do is solve for dz over dt. So we'll divide both sides by 1,000. Just notice here, you can just mark out those zeros. You got 12 over 1 dz over dt, which is 12. So dz over dt is 12. Alright, now the deal is, what units are we using? Feet? No, that would just be dz. Or, I mean, actually not dz, it would just be z, or x, or y. That's in feet. dz over dt is dealing with time, so feet per second. So this is 12 dz over dt. 12 feet per second. Alright. That's the rate of change, or the rate at which the observer and the balloon are apart from each other. How this balloon is constantly rising, so it's going to be constantly rising. So at the moment that it reaches 800 feet, the man is already standing 600 feet from where it took off, okay, from where it left, from that spot where it left. So at that moment, that's That's what we're trying to see. What is that line of sight? Some people call it the line of sight. In this case, is how far is it from the balloon to the observer, from the observer to the balloon? Okay. How fast is that rate? What's the rate of that? Not so much how far it is. It's 1,000 feet. But what's the rate now? 12 feet per second. That this dz over dt is changing. Okay. Alright, that's basically what you're looking for. Alright, hold on before I close. I want to review just a little bit. What did we do? Okay. This thing is wasting time. Okay. What did we do? Alright. Again, bear with me. I'm in tight quarters here. We looked at, first of all, we found out that the balloon was rising. So when we said at this vertical, that is dy over dt. Horizontally, we're not moving, so dx over dt is 0. And this is what we're observing here. What are we trying to find? We could find z. That's probably what you need to do first, is find the value of z. Then, if you wanted to, take that derivative. Now remember that the 2's were here, but we could divide all through by 2. We could have left it there, but I like to divide out on that. Okay. Then once we got there, and it's the same thing, the same idea with the ladder type problem. So be aware that that's the same idea. Okay. And then once we got, oh boy, I appreciate your patience here. Okay. Once we got that and found this distance here, we could plug that in. This is 0. We figured this out. We divided both sides, so dz over dt is 12. You cannot leave it as 12. If you have units, you have to put the units down. Okay, feet per second. If you're just dealing with distance, that's feet. If you're dealing with rate or rate of change here, okay, the rate is feet per second. Okay, and so that's what we have. Alright, that's all I have for this one. We will talk about part B, which I really am excited about part B. There's a couple ways we could do part B, but anyway, this is something that you need, especially when you're dealing with related. That's one of a good related rate problem, probably a good first related. Well, probably on into it a little bit more, but. This is a very good related rate problem. Alright, anyway, KP the Math G signing off. Ladies and gentlemen, if you have not subscribed, please do so. If you would like to make a comment, please do so. Even if you comment something that, well, I might not want to read, still comment on it, because I want to do better. I want to be my best for you. If you make a good comment, I just put a big old smile on my face. If you hit that like button, I'll really smile. But if you don't do any of that, it's not for my glory, but it is for yours. And anyway, so thank you so much for your time. And so, ladies and gentlemen, having said everything I'm going to say, have a great day. It makes my wife know that I'm through. No, that's my signature clap.